All right. Hi, everyone. In this video, I am going over the physics journal about elastic potential energy. So as we take a look at this, our guiding question for this is a compressed spring is used to launch a coin into the air. Where did that energy come from? So obviously the coin has energy because it's going to have kinetic energy as it's moving through the air. It's going to have gravitational energy as it goes up into the air. Where did that energy come from? Obviously the spring. And remember that spring energy is called elastic potential energy. The word potential energy just means stored energy. So the big idea is the further a spring is stretched or compressed, the more elastic potential energy, which we use in EEL, right? Capital E for energy, subscript EL for elastic, is stored in it. Remember, the potential just means that that energy is basically stored or waiting to be released. So from the Hooke's Law lab, we were making a spring or a force versus X graph, and those turn out to be linear for a spring, and just showing that the force gets greater and greater and greater the more you compress that spring. So energy is measured in joules, so aka Newton meters, which are the same units as the area underneath the graph. The reason that would be is because if you were looking at the area of this graph, it would be, well, it's a triangle, right? So it'd be 1/2 base times height. The base would be measured in meters, the height would be measured in newtons, and so that's going to give you newtons times by meters as your units. And so the area, the physical area of the graph, which in this case would be a triangle, gives you the energy. And that's true for any force versus x graph, is going to give you the energy. So the area under a force versus x graph gives you the energy stored in that thing. So when we go to gravitational energy, we can use this, we'll use the same idea. So let's take a look at this. So the area is a triangle, right? So that's 1/2 base times height. Um, The base is the stretch, how far you stretch it. The height would be the force that you apply. We can then substitute in Hooke's law, which is the force of a spring is equal to k times by x. And so we can plug that in here. Basically, I just changed the f into a kx. That's going to give you an x times by an x. And so two x's multiplied together is going to give you an x squared. So the equation for elastic energy is actually 1/2 kx squared. So So let's go ahead and take a look at one of the example problems here. So here we go. There's our example problem. So consider a spring with a 250 Newton meters spring constant. It says calculate the energy stored when compressing the spring 5 centimeters. Okay, so we got our equation. Elastic energy is equal to 1/2 k x squared, where x is how far we stretched it, k is the spring constant. So that's going to be 1/2 times by 250. And then the thing is, x does need to be in Newton or in meters. So I got to change that to 0.05 meters, right? You got to divide by 100 because there's 100 centimeters in a meter. And that is going to give you, a second here, 0.5 times by 250 times by 0.05 squared is going to give you 0.3. We'll just give you all of it. 0.3125 joules. So we obviously could have rounded that. Okay, part B, and this actually is not going to show up too much more, but just to show you that it's not linear, I'm going to give you this question. Again, I don't expect this to really show up on very much homework or anything like that, but it says calculate the additional work stored in the energy when you compress it additional 5 centimeters. Okay, so let's try that. So that means we're basically stretching it from 5 centimeters to 10 centimeters, right? So we know that when it is stretched 5 centimeters, we are storing that much energy in it. So let's see how much energy is in it when we stretch it 10 centimeters. So the elastic energy when we stretch it to 10 would be 1/2 times by, again with the 250, times by 0.1, because 10 centimeters, you divide by 100, you're going to get 0.1. That's going to give me the elastic energy is equal to 0.5 times by 250 times by 0.1 squared. And that's going to give me 1.25 joules of energy. Okay, so at 10, uh, 10 centimeters, it has 1.25 joules worth of energy in it. But the question is not asking how much energy does it have at 10. It says how much additional energy. So meaning how much energy did we add when we went from 5 centimeters to 10 centimeters? So if this is how much I have at 10, then I need to, the additional energy would be the amount of energy it had at 10 centimeters minus the amount of energy it had at 5 centimeters, because that's going to give me the additional energy, like how much I added, right? So that's going to be 1.25 minus 0.3125, and that's going to give me 0.9375 joules worth of energy. And that's how much additional, which is kind of a weird way to add that. However, right, just real quick, let's take a look at this, right, just for funsies. 0. Let's take this number, 0.3125 times by 3, and you'll note that that gives you 0.39375, which is that number. And why is that? Let's take a look at this, right? So here's our graph, right? Note there's no labels on the forces, but that's okay. So let's just say that the amount of energy stored in the spring is, right, when you have it 5 centimeters, is going to be a triangle. So let's just draw the triangle in here. Okay, so let's see. So that's when we do 5 centimeters. So let's see how many times when I stretch it to 10, right now it's going to fill this huge big triangle. But if we take a look at this, that triangle is going to fit in there 3 more times, right? Each time 0.3125, right? Each one of these is 0.3125. So anyway, we'll note that, like, right, you've doubled the amount that you've stretched it, but that's actually added 4 times as much energy, or an additional 3 times as much energy, right? We added 3 times as much energy um, by stretching it twice as far. So what's the point of this? The point of this is to show you that, like, when you add the energy, it doesn't, like, if you double the stretch, it does not double the amount of energy. In this case, it actually quadrupled it 4 times the amount of energy we added. So that's the point of that question and why that's there. Okay, thank you for watching the elastic potential energy notes. And as always, let me know if you have any questions.